the first criterion, and the overall criterion is you want to make as much product as you can, as cheaply as you can, in common sense. So as much product as you can, as cheaply as you can. If I have more than one elementary reaction going on, more than one reaction, then the first thing I want to make sure of is that I'm getting the right product. That is, if I have more than one reaction, my reactant might go to product, the product I want, or some product I don't want. So for example, you remember we looked at reactions in parallel and reactions in series. So when I have reactions A goes to R or A goes to S, P, for example, if I want to get S, then the first thing I need to worry about in my choice of reactor is one reactor going to favor production of S over R and T relative to another reactor? If so, that's the reactor I want, one that makes the right product. Similarly, or if I have reactions in series. Again, if I'm interested in R, then I want to, if one reactor is more favorable for R, then that's the reactor I want. Sorry, I thought there was something else I wanted to do, but I didn't see it later. All right, anyway, I'll worry about that later.
So is that part of why like it's important to know what's conserved and what's not, so that you can more or less determine what you're going to have compared to initial as opposed to as something?
It's always important to know what's conserved. That's basic from the kinetics. It's just always important. Right now, I don't want to, I'm mentioning this, right? We're going to get to it later. Best thing is to wait until I get later. Okay, so the first issue you have is when you get the right product. That's your choice of reaction. So now, of course, that's a complication. If you have multiple reactions, you have this complication of what am I going to get the right product? So what I'm going to do is I'm going to postpone discussion of this until later, because again, when we have lots of complications, I want to start with the simplest case. Let's understand that, and then we'll put this complication back. So, assuming if there's only one reaction, only one stoichiometric reaction, then this is not a problem. This is only one reaction, only one stoichiometry. It's only A goes to R. There isn't a second reaction. There aren't three reactions. Then this is not a problem. Then the only thing I need to worry about is a most efficient reactor. What does most efficient mean? Then I just want to minimize tau 0 or maximize X out, depending on what the criteria are. I can't do both. Remember, I just erased it, unfortunately, but we had tau 0, which has CA0, V, and FA0, X out, the specs, and the chemistry, and the kinetics. All of these are going to be given except for one. If tau is given, then I want to get the highest purity product, biggest X out, the highest conversion, the highest conversion. If X out is given, if the specifications of the conversion are given, then I want to minimize tau 0. How do I minimize tau 0? That means either the smallest reactor or the biggest FA0. CA0, V over FA0. Tau 0. Minimizing tau 0 means produce the most product, the most flow rate, or do it in the smallest reactor. Why do I want to keep the reactor small? Well, the smaller the reactor, the cheaper it is to build, in general. The same reactor, a big one, is going to be more expensive than a little one, which is more material. Now, particularly if it's a reaction that has something very aggressive chemicals. The aggressive chemicals, there's a plasma involved, if there are harsh acids, then the materials to make the reactor are going to be expensive. So if I make a smaller reactor, I need less of that expensive material. But typically what I want to do is either minimize tau or maximize x. So minus x is fine. Okay, so let's look. Now, of course, this is again with one stoichiometric reaction. So I'm taking away the complication of multiple reactions. So we're looking at one stoichiometric reaction. One reactor, isothermal, ideal reactor. All these assumptions. You want to understand this, then we'll take away one assumption at a time. And single phase. So these are assumptions, and we want to understand this first. This is hard enough. We'll take them away later. Okay, so what are we going to examine now in the next 15 to 20 minutes and the next few classes? We're going to try to understand thoroughly single CSTRs and single plug flow reactors, and then we're going to try to understand thoroughly multiple reactors, multiple CSTRs, series parallel arrangements, plug flow reactors, series parallel arrangements. And then we're also going to introduce recycle streams. You know what a recycle stream is from 228? We're going to see how that affects the performance of these reactors. Okay, so let's look now at the CSTR versus the plug flow. Let's just compare one reactor, single reactors. Versus plug flow. And let's do this for one particular type of reactor, for an nth order reaction. Linear volume expansion. So let's go to our sheet. Make sure to bring the sheet. And I'm going to compare tau of the CSTR to tau of the plug. Tau of the CSTR in general. It's general. Well, let's do linear volume expansion. So we're talking about the bottom row, the second column versus the third column. So I've got CA0, XA out, minus XA in, divided by. Now it's divided by minus RA out. If it's an nth order reaction, what is minus RA out for an nth order reaction? Who's that to? An nth order reaction. KCA to them. If you don't know the kinetics of an nth order reaction, I can't help you. Okay, so K and CA to the n. CA, we said, was CA0 to the n, 1 minus XA over 1 plus XA out, epsilon A out to the n. So that's what I get for an nth order reaction in this case. And then for CSTR. Now I look at the plug flow reactor. Plug flow reactor, I have the bottom right. So I have a CA0 integral from XA in to XA out. By the way, I can't say this enough. Half the people I call on, I can ask them their name. As soon as I point to them, they freeze and they don't know what to say and they think I'm picking on them. Remember, when you get a job, assuming you get a job, your boss is going to ask you questions, and you better know your name, and you better know the answer to the question. So get used to it. DXA over minus RA. So that's K CA0 to the n times 1 minus XA over 1 plus epsilon A XA to the n. But remember, this is continuous in the sense that the thing I'm integrating, the integrand, 1 over minus RA, is varying with position. So if you remember, if you look at the picture, in the plug flow reactor, minus 1 over RA versus XA, in, out. We said that the curve for an nth order reaction, n positive, goes up. So for the plug flow reactor, tau 0 is the integral under the curve. And for the CSTR, it's the right endpoint. Now CSTR. What can you see from the picture here? Is this ratio going to be bigger than 1 or less than 1? Bigger. Why is that? Because the pink area is bigger than the white area, and that's because the curve is going up here. And I'm evaluating it at the output. Why is the curve going up? Again, remember, an nth order reaction, if n is greater than 0, then the higher the concentration, the higher the rate. Right? So, the higher the concentration, the higher the rate. I have a high concentration at the inlet than at the outlet. So if the rate is higher at a higher concentration, 1 over the rate is lower at a higher concentration. The inlet is the high concentration, so 1 over the rate is lower here than it is here. If the curve had gone down, then of course this would have the opposite. This would be less than 1 instead of greater than 1. So what can we see immediately? What we can see immediately is that this thing is always going to be greater than 1 or n greater than 0 for an nth order reaction. So what does that tell me? What would my initial gut reaction be? If I have an nth order reaction, what kind of reactor would you think you'd want to use? It should be no shock if I'm calling on you, if I called in him the last time.
Right, it's going to be the CSTR.
You want to use the CSTR because you want to maximize the size of the reactor, right? You want to make the biggest reactor possible.
No, I don't. I want to make the smallest reactor.
So what?
So we're going to use the plug.
So you'd want to use the plug flow reactor, if that were the only thing you had to worry about. Now, sometimes, even though according to the volume of the reactor calculation you want to use a plug, there are good reasons to use a CSTR. For example, if you have a very exothermic reaction, if you use the plug flow reactor, in one spot it might really heat up and blow up. Usually, unless you work for Al-Qaeda, you don't usually want things to blow up. So, you might not want to use a plug flow reactor. You may want to use a CSTR because you can mix it up and it's easier to cool down. Okay? And there are other reasons why you might want to use a CSTR at some point rather than a plug flow reactor. If you have problems with diffusion, which we haven't discussed yet, we will. When you mix things, you sometimes can help if you have a two-phase system with a catalyst. As we'll see later in the semester, sometimes it's useful to increase the mixing, even at the expense of using a bigger reactor, because you help the kinetics. You help the effective kinetics. But we'll talk about that much later in the semester.
Use a plug flow. It's greater than 1.
The tendency is to use a plug flow reactor because we don't want a big tau, we want a little tau. A little tau means a small reactor or a big production rate. if you decide you want to maximize tau instead of minimize tau, you might not be at the company too long. Because you're going to build big reactors with very little product coming out. And that's usually not what gets you a promotion. Okay, so why don't we plot this thing? Tau CSTR versus tau plug versus XA. And if we plot it, we get, let's plot it for different ends. And let's look at some trends here. And this is, of course, versus XA or the log of XA, the log of 1 minus XA. And this is 0 and 1, right? Oh, the log of So this corresponds to XA equals 1 and XA equals 0. I think that's right, but let's see. Okay, well, let's go through some trends. Let's look at some trends here. The first trend, as we said, we can see that from the equation, is that when n is greater than 0, so trends. 1. If n is greater than 0, then tau CSTR is always greater than tau plug. On the other hand, if n equals 0, what happens if n is equal to 0? If n is equal to 0, then the rate is independent of x, because it's k CA to the 0. So the blue line is horizontal. If the blue line is horizontal, then what's the relationship between the area of the rectangle and the area under the curve? They'll be equal. So when n is equal to 0, tau CSTR is equal to tau plug. And you can see that here, when n is 0, this term drops out, this term drops out. So this integral is just the integral dx, gives me the ratio. Just get 1. If n is negative, I have a negative order reaction in some concentration regime. Then instead of this curve going up, it goes down. If it goes down, then the right endpoint is lower than the rest of the curve. So which is going to be bigger? The plug will be bigger. The tau plug rather than tau CSTR. Now, of course, this is for an nth order reaction. If the kinetics are more complicated, I have to analyze it. Okay, now notice the second trend is that these trends say tau CSTR divided by tau plug goes up as n goes up. As n goes up, this curve gets sharper. If I have an nth order reaction, the bigger n is, the sharper the curve is. The sharper it is, the bigger the difference between the area of the rectangle and the area under the curve. So that's sort of obvious. What else? As XA goes to 0, as XA goes to 0, well, what happens as XA goes to 0? As XA out, I shouldn't say that, as X out goes to XA in. So as the conversion change in the reactor gets small, so as the base gets smaller and smaller. So instead of going from here to here, let's say I only go from here to here. If I only go from here to here, then the curve doesn't change very much. So the difference, and that's the definition of continuity. If you have a continuous curve, then if delta x is small, the curve becomes almost a constant. It's the definition of continuity. One of the way of thinking about continuity. So the difference between the plug and the CSTR gets smaller and smaller as delta x gets smaller. So that tells me that tau CSTR over tau plug goes to 1. These are all sort of fairly obvious trends. How about and conversely, as XA out minus XA in gets big, then tau CSTR over tau plug goes up. So as this thing goes up, so does tau CSTR. Because the further apart they get, the bigger the difference between the area of the under the curve and the area of the rectangle, if the curve is monotonic. We also find that epsilon A up makes the ratio go up. That's a minor effect, but as epsilon A goes up, it raises the curve a little bit, and you can see it here. And that's a fairly minor effect. And the last trend I'd like to point out is, it's actually not a trend, is that in the end, well, it's not even worth writing as a separate trend. The choice of reactor you don't make based on epsilon A. Epsilon A is a minor effect. But those are all just some basic trends. Any questions on that? Okay, so what I'd like to do is just give you a couple of issues, some sense of what happens when I have multiple reactors. We're not going to do too much of that today because we only have a couple of minutes left. But there are a couple of things that are sort of trivial. And one of them is, what if I have plugs in series? So if I have a plug flow reactor followed by another plug flow reactor, actually, dot, 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 followed by another plug flow reactor, is this something that it's sensible to build? Well, let's look at the equation. And here's where, with these kinds of problems, here's where you see why I made a big fuss about reference state. I made a fuss about the reference state because when I look at plug flow reactors in series, it's not convenient for me to use the inlet to this reactor as the reference state. I need the same reference state for all the reactors. So I might choose the inlet to the first reactor as the reference state, but that's not the inlet to the nth reactor. Okay, so reactor 1, reactor 2, reactor N. If we look at our sheet here for general, we have tau 0 for the first reactor is Ca0, and let's call this X in, and I'll call the outlet from reactor 1 X1, the outlet from reactor 2 X2, the outlet from reactor N Xn, which is the same as X out. Okay, so this one is the integral from X in to X1, dxa over minus Ra. And I'm going to put the Ca0 here so I don't have to keep writing it. And in general, tau 0 for the jth reactor The Jth reactor goes from xj minus 1 to xj. Dxa over minus R. So it's clear, hopefully it's clear that all of these design equations for each reactor have the same integrand. It's the same function, just different limits. So just for fun, let me add them up. Tau 01 plus tau 02 plus dot 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 plus tau 0n. If I add them up, they all have this, all divided by CA0. They all have the same integrand, dxa over minus Ra. But what I have is the integral from x in to x1 plus the integral from x1 to x2 plus dot 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 plus the integral from xn minus 1 to xn. Well, if they all have the same integrand, what is this integral equal to? Here's I have to. In the white jacket? I don't have it all day. High school calculus, not even college calculus. What is the integral from x in to x1 plus x1 to x2 plus xn to xn minus 1? X in to xn. So this is the integral from x in to x out, which is xn, dxa over minus Ra. If this is tau total over CA0, what is this equation here? The left side equal to the right side. What is that the equation of? Tau total over CA0 is the integral from x in to x out, dxa over minus Ra. I know how to read. What is that physically the equation of? I can read. No excuse that you can't see. You should have asked me if you can't see. What is that the equation of? Has nothing to do with vision. Yes? What plug flow? One plug flow reactor going from what conversion to what conversion?
Entering and
Okay, so what does this tell me? That if I have n plug flow reactors in series, that's equivalent to, as you just said,
one single plug reactor.
so n plug flow reactors in series is equivalent to a single plug flow reactor. So is there any reason to ever build n plug flow reactors in series? Anything obvious? No, it's cheaper to just build one big one than a bunch of little ones. Unless I have some other reason. If anyone suggests a possible reason why this might at some point be something I might want to do. I don't want to do it if I have a simple system.
If I need different temperatures between the reactants that everybody have in.
If I need different temperatures, or what other reason may possibly?
Maybe you want different reactions in different reactors.
No, single reaction.
Oh, sorry.
We're looking at single reactions.
Different concentrations, you want to pull out a different,
If you wanted to pull out different concentrations, intermediate concentrations, another possibility. Let's say, yes?
Let's say I can't achieve the desired composition from the reactor I have.
No, I can, because n reactors in series is the same as one reactor.
No, I'm saying, like, if I work in industry, they have BFR for a certain, like, I know, like, a certain.
Well, if you have the reactors in the basement and you don't want to build one, and you want to just use what you have around, you may want to hook them up. Another possibility is if you have a highly exothermic reaction or a highly endothermic reaction. If it's highly exothermic, in a single plug flow reactor, you might not be able to cool it well enough. You might try to wrap a heat exchanger around it, but that might not be effective enough because the heat transfer coefficient of the material may not be high enough. If so, you might want to put intermediate cooling in, or intermediate heating. Okay, so that's it for today. We'll meet on Friday. I'm gonna photocopy this now and put it in my box. And the test is.
book or what?